Hi there, Math 126 students. Wanted to make a little supplement on the distance to a plane from a given point. This is a topic that we used to do a lot on, and then it just took a lot of time, and so we didn't do much. But I noticed this quarter the department inserted one question on it, and it's about this formula. Now, I just made a separate video about using the ebook. You know, if you ever find yourself, you get to a homework question, here's the 12.5 homework, you're scrolling through and you're like, okay, you did that in class, you did this in class, and then you get to a question that maybe doesn't look like something I did in class, or doesn't look familiar. One of the first places you should look is the textbook. Hopefully you already looked at the textbook. And if you did, you would see the formula sitting there. That's how we used to do the homework before YouTube and everything. We would just flip back into the textbook and see. And this is the 12.5 section. So if I was a student, and it's about, you just have a few pages to flip through. There's the discussion of lines. I mentioned in my previous video, it's really nice to click on these animations. If you're having trouble visualizing something, some are interactive, some aren't. This says, I have a point. I have a vector parallel to the line. We move it over. We rescale it. We draw this line. Okay, that's what we did in class. So those are nice little extra things. There's the equation of the plane. There's all sorts of interactive components. Page 2, page 3, distance. So those, it would have taken 3 pages of flipping through, and you would have the formula, and then you could just do the homework question. It just says plug those things in. But I wanted to make a video where I talk a little bit about where that comes from. But I'm just making a comment of a lot of answers are in the textbook. That should be one of your primary sources. Oops, well, it's a different question. Doesn't matter. So ultimately, the problem tells you what to do. But let's say a few general things here. Okay, so what is this saying? This question is saying you have the equation of a plane like this, and the equation is written in this form. So unfortunately, when you use a formula, you do have to match the form. So it says assume everything is on the same side. This side is 0. And everything is expanded. Now, it doesn't have to always be like that, but it's saying assume you have that. And you have some point they're calling x1, y1, z1 that's not on there, and you want this distance. This is a formula I don't use very often. I often don't remember it, to be honest, because I have another way I can do it. If I had to do this question, what I would do is I'd find the equation of this line. And that's actually not too bad to do because we already have a vector that's perpendicular using the same normal vector. And then I would find the intersection point. And then once I know the intersection point, I would do the distance between those 2 points. That's how I would solve this if I didn't have a formula. But I'm going to tell you a little bit about where this formula comes from because it's kind of interesting. This is more just a case study and getting to think in 3D and using some of our tools. Okay, so here's the clever idea. So the clever idea, and then we'll do that example. But the clever idea that gets us to think about a few things is if you have a plane and you have a point right here, x0, y0, z0, and you have a point that's off of it, x1, y1, z1, and you go straight down. There's a little comment that we have this normal vector. And that normal vector is this A, B, C. I know I'm doing this in general, but just stick with me for a second. It says, okay, if you had written the equation of the plane, which we talked about last time, it would look this way. B, y minus y1, z0, y0, sorry, z minus z0 equals 0. Okay, so here's the clever observation, which is when we're trying to find this length, both these things are perpendicular. We really want to find this length right here, however far that is. The truth is we can take that normal vector and draw it wherever we want. So in fact, we could draw it right on top of this. Let's do that. There's our n. So that's the length we want, is this length. And there is a way to think about it as a projection. And it's a clever idea, basically, to draw this vector from the point we know on the plane to the point we're dealing with. Let's just walk from there to there. Now, that is not the correct distance, but we can find that vector. How do we find this vector? We do a subtraction. We do x1 minus x0, y1 minus y0, z1. And this is not an essential part of the course. It's just more of a chance for us to think in terms of vectors. So that would be that vector. But that's not what we want. We would like to know how much of this vector is in the n direction. And the moment you see that, you go, it's a projection. It's a projection. You say, well, they aren't tail to tail, but if you drew them tail to tail, it would look like this. You would have n this way. You would have this vector this way, this one here. And what we want is this projection. So that's the only thing that's real. The reason the department has this question, the reason we used to do more with it, is just it was a chance to connect what we've been doing, that's the length, it's the projection. And the moment you recognize something's a projection, you go, oh yeah, we have a formula for that. It's the component projection of, we're projecting onto n, and we're projecting x1. So that's what's interesting about this is, if you ever find yourself in a situation where you're like, this could be answered with a projection, this is the answer. Now, we usually put absolute values around this because this could be negative if it's below or positive if it's above. But as soon as we're here, we're done, because the projection is a dot b over the magnitude of a, which is the thing you're projecting onto. And so we need to do the dot product of these two things, which would be a times x1 minus x0 plus b times y1 minus y0 plus c times z1 minus z0 all over the magnitude of n, which is going to be the square root of. And now you can see where the formula is coming from. But there's one added little, thing to this, which is, okay, what in the world is this d? Well, the d is the thing you would have gotten if you had expanded all this out. Sorry, I don't know why I wrote that one there. So this is, like I said, this is not, you don't need to know this proof. This is just kind of interesting. It's a chance to see a projection in action. If we expanded this out, this is ax plus by plus cz. And you have all this other stuff. Negative a, x0, negative b, y0, negative c, z0 equals 0. And this right here is your d. So d is negative a, x0, negative b, y0, negative c, z0. But if you expand this out, that's exactly what this is. So this thing here is ax1 plus bxy1 plus cz1 plus d. And you don't even need to know what the starting point was. That's kind of surprising. So this is a projection, is the point of that. Absolute values are there to make the top positive. That's it. I just did the visual, but this is what they're doing. They're projecting. So in terms of the formula, and again, I don't use this enough to have it memorized, but if I was doing the homework and I was a student, I would have looked, get to this question, we go, okay, we have this formula that says ax1 plus by1 plus cz1 plus d over the magnitude. But in order to use it, we have to have the equation in the form that matches. This doesn't quite match because the 8's on the wrong side. So you need to write it this way. Minus 8 equals 0. And then you say, okay, this is A, was 1. This is B, negative 2. This is C, negative 4. And this is D. And the surprising thing is you just plug your point into that equation. It's not going to be 0. Otherwise, it'd be on the plane. So it's going to be 1 times negative 3. Use a different color so you can see this. 1 times negative 3 plus negative 2, that's B, times 8, because that's the y coordinate of my point. And then plus negative 4, that's my C, times the z coordinate of my point, which is 6, plus the d is negative 8. And I'm going to take the absolute value of that, and I'm going to divide by the length of the normal. So 1 squared plus negative 2 squared plus negative 4 squared. But ultimately, that's a projection. That's what's going to go here. And we could simplify that. Negative 3 minus 16 minus 24 minus 8. Negative 19, negative 32. 51. The absolute value would be 51. So I'm getting 51 over. So if this is wrong, don't tell me. I'm just trying to, the point of this video was just to show you. But that's that distance. As I said, that's not probably the way I would do this. If I encountered this 5 years from now and hadn't taught this course recently, I might remember that's a formula. But I personally would probably just find a line that's perpendicular to the plane that goes through my point, and then I'd find the intersection. But that's a nice little exploration of vectors, and here's a cool spot where projection comes up. So basically a formula to know and add to your note sheet, but not a major part of the course, but I hope that was kind of interesting. Okay.